Hubble parameter. It's just times minus G tilde 0, 0 inverse. Okay, and the way to prove that, it's trivial to prove it. Just follow your nose and calculate the affine connection for this thing, assuming that G tilde is a constant. You get this result, and then plug that in and calculate the Riemann curvature tensor, and guess what? You get this form that tells you that it's locally de Sitter times this constant, which for exact de Sitter would just be h squared, and now has an extra minus G tilde 0, 0 on it. So this is just de Sitter with a slightly different Hubble parameter. That means that all of these results that I had before, that I used before, namely, well, let's see, way back. Here, you just take the h squared and you replace it by h squared times minus G 0, 0, and it's easy. So, so for example, suppose we look at the stress tensor induced by a massless minimally coupled scalar on quantum gravity. So we want to integrate out these differentiated scalar fields. They would normally screw up the proof of the Stravinsky formalism. We integrate them out, and what we get using those results, and what we get is this. Actually, if you assume that this is just a constant, that has the form of a negative contribution to the cosmological constant. And let's notice, by the way, that G tilde 0, 0 could be arbitrarily big. So that's I think, really interesting. And second, how about curvature-dependent renormalizations? How does that work? Well, the one-loop counterterms has been known since the days of 't Hooft and Veltman, are c squared and r squared. The c squared term is fundamentally higher derivative, and that means it's just irrelevant for large logarithms. But the r squared term contains a piece which is interpretable as a renormalization of the lower derivative counterterm. What you do is to subtract off the part that would cancel the classical value of r, which in dimensional regularization is d times lambda. So you write r squared as that, and that's an irrelevant higher derivative counterterm. And then this, which could be interpreted as a renormalization of Newton's constant, and this, which could be interpreted as a renormalization of the cosmological constant. And that's how the Kalin-Zemanzik equation is going to work. Okay, well, that's in an overview how it all works. Let me see how I'm doing on time. I guess I've still got 15 minutes, so I'll go over this. There are, of course, a few issues left. So I hope I've made it clear that, that number one, this combination of the renormalization group with Stravinsky's stochastic formalism is the way to go. It's right. There's just no question that it's right in nonlinear sigma models, and it has a fairly straightforward generalization to quantum gravity. However, quantum gravity is not quite the same as a nonlinear sigma model. That's why we studied it in the first place. And that means that there are some issues left to solve. And of course, I make jokes to my graduate student that's why they pay us the big bucks to do this. So let's go over these issues. So the first is combining renormalization group and stochastic formalisms. At one loop order, every logarithm is either stochastic or renormalization, but at higher loops, there's going to be mixing between the two effects. You might worry about how that works. I think I know the answer to that. I think the answer to that is that you just use the renormalization group to improve the original stochastic equation, and then you forget all about it and just use that stochastic equation the way you would have used it with Stravinsky. You can check that explicitly by doing two-loop calculations in nonlinear sigma models, and I think that should be done to assure us that that's right, but I think that that's right. Second issue is something that doesn't even occur in nonlinear sigma models, but does occur in gravity. And that is, you remember this induced stress tensor that I got for massless minimally coupled scalar. So that's only going to be constant, or only going to be conserved if this G mu nu tilde is constant. If it isn't constant, and of course it won't be when you use it to solve the stochastic equations, there's going to be slow time evolution, then it's not anymore conserved. Now, that is not wrong. That is exactly right. It comes from making the leading logarithm truncation. Remember this stress tensor for lambda phi to the 4 theory. If you look at the induced energy density and induced pressure, they really do obey conservation. Order by order in perturbation theory, it really is true. However, if you just keep the leading logarithm terms, at two-loop order, the log a squared and the log a squared, and forget about the subleading logarithm term, then p is just equal to minus rho, and conservation fails, because see, this term would be 0, but that term isn't 0. Okay, so this is just this failure of conservation is an artifact of doing what we wanted to do, which is to take the leading logarithm approximation. So this is not an error. It's completely right. It's an artifact of the truncation that we made, but it still does leave us with a problem. There are 10 Einstein equations, and the failure of conservation means that 4 of them are not going to be true. They can't possibly be true. So what do? Well, 2 possibilities are either you identify some combination of 6 of them that you take seriously and solve those and then just ignore the other 4, or it could be that you want to look more carefully at this induced stress tensor and extend it in some way to make it conserve. And I don't know which is the right way. I suspect it's likely this way, but I don't know. In any case, that's something that doesn't even come up for nonlinear sigma models, but certainly does come up for gravity. More issues. Well, another issue that didn't come up for nonlinear sigma models on de Sitter background, because the background is non-dynamical, is what becomes of the constant de Sitter Hubble parameter for a general h of t in those 2 key dimensional regularization relations that I told you, the coincident first derivative of a propagator and the coincident second derivative of a propagator. So those h squareds, what happens to those? And I suspect that they are not even likely local. I suspect that one factor of h squared becomes r over 12, and another one is just not even local. That's what I think is true. And I actually have a summer project with 2 University of Florida graduate students to just work that out. You won't be able to get exact results, but you can get very good semi-analytic approximations. And I think that one's under control, although I don't know what the answer is yet. Another issue, which is more vexing, is understanding the non-covariant counterterms which arise. So we've done about 10 graviton loops, I think. These are very, very hard calculations on de Sitter background. And 9 of the 10 were done in the simplest gauge, which is one that Nick Samus and I devised way back in 1992. It breaks de Sitter invariance, and that means that it is going to induce non-invariant counterterms. We thought that, and it does induce non-invariant counterterms. We thought that those non-invariant counterterms were only coming due to the non-de Sitter invariant gauge. It turns out that that's not true, and we actually stumbled upon that. Let's see, Dražen Glavan, Shunpei Miao, and Tomislav Prokopets and I stumbled on that by doing the only case where a graviton loop was calculated in a de Sitter invariant gauge. And that was, we recalculated the vacuum polarization. It's a lot harder to do it in a de Sitter invariant calculation. You don't want to do that, but I think we did it right. And at the end, we still found the same stupid non-invariant counterterm we needed. And we were so puzzled by this about why it was happening. We think it's coming due to the time ordering of the Schwinger-Keldysh form of interactions in the Schwinger-Keldysh formalism. So the thing that breaks covariance is that the functional integral formalism doesn't give you, normal ordered interactions or any other ordered interaction. It gives you time ordered interactions, and we think that's what is fundamentally breaking general coordinate invariance and causing non-covariant counterterms to arise. So this is not wrong. it was known way back. I think Bryce DeWitt guessed it way back in the Trilogy paper in 1967. It never previously came up in dimensional regularization in any kind of analytic regularization. And it is only occurring on curved space backgrounds. But it for sure is there, and we have to make sense of it because, part of our technique is using the renormalization group, and you have to be able to understand how those non-covariant counter terms are going to change the Callan-Zemanzik equation if they change it. And again, I don't know what the answer is. I suspect that that these terms actually can be absorbed by something else that Bryce DeWitt talked about way back in 1967, which was the functional measure factor. So in the functional integral formalism, it's really not dg mu nu, it's really dg mu nu times some square roots of minus g and g zeros and things like that. You can see that pretty clearly in the canonical formalism, in using the canonical formalism to derive the covariant functional integral formalism. This never previously affected anything with invariant regularizations, but it for sure is happening right now, and not just in this theory. And we have to solve this. Another problem is eliminating gauge dependence. So it turns out that the effective field equations, of course, are gauge dependent, and in order to know that you're calculating a physical result rather than just gauge artifact nonsense, you have to be able to get to purge that gauge dependence. We have a technique for doing that, which involves taking careful account of the quantum gravitational correlations from the source which disturbs the effective field and from the observer that measures that source. And that's a long, and we've applied that to two separate systems in flat space background and then calculated them in a general covariant gauge and shown that the gauge dependence explicitly drops out. We are going to this summer, we, by the way, is Dražen Glavan, Shunpei Miao, Thomas Olper-Kopf, and myself. We're going to redo that calculation in the Jitter background, and I expect that the result will be the same. The bottom line is that what has always happened before is that whatever large logarithms you get might have different numerical coefficients, but they always will still be there. And that's what I think will still happen. Although, again, statements like that are all the better for proof. It turns out that this same seminar series will host a talk by my collaborator and wife, Shunpei Miao, who will be speaking here on June 2nd. So she will describe that technique in detail. Okay, and final issues. I'm right at the end of the list of issues now. And this is, again, stuff that doesn't happen in nonlinear sigma models, but does for sure come up in gravity. And that is, what about the constrained components of the metric? So as everybody knows, the 10 metric components break up into 4 which are pure gauge, plus 4 which are constrained. They're not 0, they're very important. For example, this is one of those constrained components. And then 2 dynamical gravitons. Only the dynamical gravitons have their own stochastic jitter, but the 4 constrained components do depend on the stochastic jitter. They start out depending quadratically and then have higher order terms. This, I think, is a very, very important effect because notice that G00, corrections to G00, which will be, basically like the Newtonian potential. If you imagine the steady buildup of stochastic jitter, that's going to eventually drive the universe to the point where it has so much energy density that it lies within its own Schwarzschild radius, at which point G00 will be driven to 0. And that means that the inverse G00 is going to go to infinity. And guess what? Remember in our induced stress tensor, that involves there. So it's a negative contribution to the cosmological constant that gets arbitrarily big if G00 goes to infinity. So this is exactly the kind of thing that can do that. So I think this is a very, very important effect. We have to get this straight. Finally, we need to model the effect of the constrained fields in terms of non-local gravity. So after the end of inflation, there's not going to be any more stochastic jitter, but the constrained fields don't just drop to zero. They still depend on integrals of the past jitter, of products of the past jitter. And although that's right, it's pretty inconvenient to look at it that way. And it would be easier if you could model those effects as non-local modifications of general relativity. For example, one of the basic stochastic effects, which I think was first derived in 1982 by Larry Ford and Alex Vilenkin, Alexei Starobinsky, and Andrei Linde separately in 3 separate papers. They get that the VEV of the square of a coincident field, a scalar, massless minimally coupled scalar, is h squared over 4 pi squared times logarithm of a. What is that? That's on the Jitter background. What is that for a general background? Well, nobody knows, but one possibility is that it's 1 over the covariant D'Alembertian acting on r squared. This summer project that I have with the graduate students will actually look at this and develop this kind of stuff more exactly. Factors of logarithm of HR, which have figured in some of our discussions, can be looked at as 1 over the same covariant scalar D'Alembertian acting on 1 over delta 3 of x. So what we want to do is to model these effects as non-local modifications of gravity. And once you have such a model, then you just forget about where it came from. And if you want to study late time physics, you just use that non-local version of gravity the same way you would have used Einstein's equations. Okay, so what might emerge from all of this? Well, nobody knows. It's obvious that perturbation theory is breaking down. Nobody knows what happens after that. It's not clear at all that anything big happens at that. It could be that you've got the series of 1 minus x plus x squared minus x to the third. And it sums up to 1 over 1 plus x, and at x equals 1, it just goes from value 1 to value 1/2. It's a change, and it's a non-perturbatively large change, but it's not, in the scheme of things, a major change. Or it could be that it changes physics all out of bounds. The reason for doing this project is to try and figure out which of those 2 possibilities it is, and if it's the second, figure out what those changes are. So I don't know, but let me give you 3 possibilities. First is that this kind of thing could give substance to lambda-driven inflation. So that's the idea. Everybody knows how usual inflation, or sort of brand X inflation, is driven by a scalar inflaton. Everybody, I think, is aware of the sort of naturalness problems associated with that in getting inflation even to start in the first place, et cetera, et cetera, et cetera. Perhaps that's all just not a correct way of thinking about it. Perhaps there isn't any scalar inflaton. Perhaps there's just general relativity with a large cosmological constant. That is exactly the thing that we usually regard as something that has to be explained away. That would be a beautiful way of starting inflation. It would be completely natural. Nothing is as spatially constant as a constant, and that would get inflation to start. Classically, it would never stop, but I think I've convinced you that it's likely that there's going to be quantum back reaction effects which will cause it to slow down. So suppose in this model, it starts and it persists for a very long time until eventually G00 is driven to 0, which induces a negative, arbitrarily large change to the cosmological constant, which stops inflation. That would, I think, be really neat. Another possibility has to do with what happens to that same model late in cosmological history. I'm going to try and get a mosquito here. Got him or not? Tried. You remember this issue about what happens to the factors of h squared on de Sitter. Suppose one factor of the h squared on de Sitter turns out to be proportional to the Ricci scalar. Ricci scalar is a very, very special function of H and H dot in that it happens to vanish during radiation domination. So if you assume that H is going like 1 over 2T, R just exactly vanishes. And that means that this effect would build up and build up during inflation, then it would go quiescent during radiation domination. And so for most of logarithmic cosmic history, it would just stay zero. There'd be no change in anything. And then very, very late in cosmological history, matter domination would come on, and that would trigger a very slow, logarithmically growing late time effect. Perhaps that could be used to explain the current phase of cosmic acceleration. Finally, in some of the many results that I presented to you, you see that forces change. In particular, the gravitational force changes. Now, again, I want to stress, it changes by a non-perturbatively large amount. Nobody knows what happens when you sum up those logarithms. Maybe it sums up to just nothing very big, and you can absorb it into some renormalization, and late times it's no different at all. But maybe some part of that change survives to late times. And maybe that's giving rise to some modification of gravity on large scales. It would be a modification on large scales because it's being caused by this ensemble, this vast beyond imagining ensemble of superhorizon gravitons, which provide a sort of a gravitational vacuum polarization, which is modifying the gravitational effects of Einstein gravity. And maybe this could be a relativistic version of Milgram's modified Newtonian dynamics, which works so well to explain galactic structures. So those are 3 possibilities. And at that point, I think I'm done, and I will just conclude here. So inflationary gravitons affect gravity and other forces. They manifest by large logarithms, which cause perturbation theory to break down. I think I've argued to you, I hope successfully, that you can resum them by combining together a variant of Starobinsky's formalism, where you integrate out differentiated fields in the equation of motion to get a curvature-dependent effective force, and a variant of the renormalization group, where you take the counter terms and you regard some class of them as being just curvature-dependent renormalizations of bare parameters, of terms that were originally present in the Lagrangian. And this all can be, and we are trying very hard to apply this to the great problem of resumming graviton logarithms, which is going to give rise to some kind of non-local effective field equations. And it has, I think it's pregnant with possibilities. So I will end there, and thank you for your attention.
Okay, thank you very much, Robert, for your very interesting talk. I see that Alexei Starobinsky would like to ask a question. Alexei, please.
Okay, actually, let me first thank Richard for this very interesting and very informative talk. And actually, my remark, it's not critics, it's rather remarks and maybe just proposals for the future investigation. First, I would like to mention, when in case of minimally coupled scalar field, in some regime it's possible to check the stochastic formalism, just directly make the same calculation in the standard observative quantum field theory and compare the results. In particular, this is possible if we have lambda phi 4 interaction and m squared small, but not too small, m squared much less than h squared, but m squared much more than h squared multiplied by square root of lambda. And in particular, it is checked now up to 2 loops, and not only for average values, but for many controllers, and I just want to mention just a recent paper by Sasha Kamichik, Teresa Vardanyan, and myself, which was appeared in Archive in September last year, and it is now just a few days ago. It was published and it appeared in EPJC. So up to two loops, it's possible to check under some assumptions about coupling.
Thank you. I'll take a look at the paper. Thank you.
Yeah, about coupling constants, it's possible to check that indeed stochastic formalism gives essentially the same result as a standard field theory. But that's why it's interesting to look if there exist similar cases in these more complicated models about which you spoke, particularly with additional vector fields and so on. So the question is, it would be indeed interesting to find some regimes in which it's possible to not only to use stochastic formalism, but also to make the same calculations using standard field theory, quantum field theory, and check that they indeed, let's say, at two loops, up to two loops level, and possibly even higher, they give the same result. So once more, it's a proposal for future investigation. Second remark, it's you didn't mention, but actually there exists some other proposals. So I think that we should remember about it. You always assumed that we have naturally defined adiabatic vacuum in Poincare wedge, in the so-called Poincare wedge. But well, in principle, it's not the only possible proposal. It's natural proposal inside the path-light cone of any observer, but outside the path-light cone, in principle, one can consider additional terms, which, though they are still decaying at large scale, still it's possible. And there are some papers with a statement that in this case one can obtain even some additional type of divergence. But of course, in all these cases, the natural question is this new initial conditions, are they physically realizable? A reasonable way would be to consider the full de Sitter with the finite but still some stage of contraction, and consider if it's possible to have something different from that initial conditions which both you and me used in our papers. So once more, it's a possible. Then the simplest variant, in which we know that though that result is different, nothing but appears, is the so-called elliptic de Sitter. If you simply identify two opposite points in the full de Sitter map. Okay, and my final remark. Once more, so it's not a critic. It's a proposal for possible proposal for future work. And one and final remark, just which though, as you correctly said, we don't have clear understanding what happens in the case of quantum gravity in the de Sitter. So produced by cosmological term, and I shall make one more remark about what happens if this cosmological terms is time dependent. What I want to say that useful information can be obtained from looking at classical solutions of the same theory. Of course, they don't contain quantum effect, but still well, already at the classical level, we can see some new effects. And in particular, okay, let's consider the exact Einstein theory plus a cosmological constant, where the correct statement is that the de Sitter is not the generic late-time asymptotic illusion. It's only a distinguished one, which has zero measure in the space of all possible illusions. And generic asymptotic behavior is only locally de Sitter. It's de Sitter inside the horizon of any observer, but globally, it's not de Sitter at all. It's in some sense de Sitter multiplied arbitrary 3 times 3 matrix of with special dependence of special coordinates were only conditioned with the special gradients are sufficiently small. So already at the classical level, it's possible to say that de Sitter is, in this sense, it's unstable, not in the dynamical sense, but in the sense that it's only for a very specific illusion. So that's why I would say that interesting problem is to consider looking at your model, at your models, and at your more complicated models. The interesting problem is to see what happens in the classical illusions. What is the behavior later behavior?
Well, I agree with you completely. You know that some of the numerical relativists are working on that idea. So there's a numerical general relativity person named Chris Stevens, who's in New Zealand. And he's what he's doing is studying the effect of putting in a train of gravitons, classical gravitational radiation, to sort of simulate the particle production that goes on during de Sitter. And he's working out what happens. And I think he has shown that you can slow the approach to de Sitter, so you can't ultimately stop the approach to de Sitter, to local de Sitter, but you can cause the density to become large enough that the universe will hold itself together for a while, and I think that's a very, very interesting investigation.
Okay, and my final additional remark, so once more to just which arises just as one of your last statement about the possibility of varying lambda, inflation with lambda depending on time. That one should be cautious. Simply, there were some some toy models proposed, in which, well, even taking some assumptions about two behavior of hypothetical, of course, to behavior of graviton propagator. Okay, and when people say, okay, we obtain the Sitter-like metric, in which say h or effective cosmological constant, which is h squared, is decaying as some power of time. So finally it will become zero, and so we obtain the decay of the Sitter to Minkowski. In particular, I saw such a statement in some unpublished paper, in some archive papers by Sasha Likov. So my remark that this is misleading. If we have h depending only as a power, as the Hubble parameter, or cosmological constant depending, decaying only some power of time, it's not the end of inflation. In our cosmological language, it is slow roll. Inflation is about end, because you can easily check that the effective equation of states still is still expression equal to minus epsilon plus decaying term up to infinity. So it's not a decay of this. It's not what we need for cosmology. So for cosmology, that we should have some more rapid end of inflation.
Okay.
Thank you.
So I see one more question. The question is from Ekaterina Pazdieva. Katya, please ask your question. Are you here?
Yes, I'm here. Thank you for the informative talk. And however, I have some technical questions. What types of perturbations consider for getting a spectral index? This is just metric scalar perturbation, or this is scalar field perturbation. And how the considering perturbations can be modified with introducing non-locality to the considering gravity model.
Are you asking the question, how would I get scalar perturbations? Is that your question?
Yes, if I understand correctly, reading some work, some authors did quantization with variables consisting not only metric perturbation, scalar perturbation metric, but also scalar field perturbation in the same variables. And what type of variables was considering in initial works to get spectral index of scalar perturbation. This is scalar perturbations of metric, or this is scalar perturbations of scalar field.
Well, so first off, let me give a disclaimer. I am not claiming that that I have a viable model of lambda-driven inflation. I honestly don't know whether lambda-driven inflation is right or not. That's just one possibility. However, if lambda-driven inflation were right, the way that you would get scalar perturbations is when you put together two graviton fields. That has to do with this issue about constrained fields. So the fundamental stochastic jitter is coming from Hij transverse traceless, and the four constrained fields, one of which would be the one which is contributing to scalar perturbations, that would be driven by quadratic terms involving Hij, basically integrals of Hij times derivatives of Hij times Hij. And everybody, I think, has known for a long time that that term is present. It's usually considered to be negligible, and it indeed is negligible, because if Hij was just strong enough to to measure, then Hij squared is going to be too small to measure. But if you're imagining a situation like this, where the effects are building up and building up and building up, you might imagine that those accumulations are getting big enough so that even an Hij transverse traceless squared term is big enough to see. So that's if lambda-driven inflation were right, that's how you would see scalar perturbations in it.
Scalar perturbations.
I'm not sure I understood your question, but I think that was likely your question. If it wasn't, please ask it again, and I'll try again.
Katya, do you want to ask more or it's enough for you? Katya?
Да-да, у меня просто звук пропал. I would like to ask how scalar perturbations related with choose of gauge, or how scalar perturbation related with gauge choosing, and how what general principle for modification of scalar perturbation if we add non-locality to the initial gravity model?
Okay, so I think your question is, suppose that you imagine a non-local modification of the Einstein field equations, how would gauge fixing work? The answer is it wouldn't change at all. So you'd still have general coordinate variance in the simplest way of doing it. You would still have general coordinate variance, so you would still get to set 4 coordinate conditions, and you would choose them as you wish. And the only difference is that instead of those things being applied to the local Einstein equations, those would then be applied to your non-local effective field equations.
Okay, thank you for the answer. Thank you.
You're welcome.
Okay, we can go for the next question. I see the next question is from Sadhasatava Brahma. Please ask your question.
Yeah, thank you. Thanks for the very nice talk, Richard. So I have a very nice question. As I'm sure you're aware, people calculated these loop corrections for the scalar perturbations for slow roll inflation. And in that case, I think the conclusion was that this kind of logarithmic effects were not, you don't find log of A effects, although that was what was initially reported, but instead what one finds is log of H over some mu, some renormalization scale, this kind of effects. So
whoa, whose work are you quoting there?
So these papers by Senatore and Zaldariaga from, I don't know if you agree with those.
I'm sorry, I don't accept that work. If you look at those papers, what they did, those papers were written in answer to a paper that I wrote with Vakifa Nemli and Imre Kyahya, and where we gave an explicit example of a situation where you would get log A growth. I don't know what part of explicit example they don't understand. What they stated, although they many times told people that our work was wrong, what they actually stated is they agreed with our conclusion, but which was that if you kept the standard definition of the power spectrum, then these effects would occur, but that what you should do is to redefine what you mean by the power spectrum observable, and then you can redefine it in such a way that you don't get these effects. And I must admit, I felt a little bit angry at that paper, and especially the way that they were publicizing it, because when Vakif and Emre and I wrote our paper originally, we were very, very clear, I thought starkly clear, to state, look, we don't know and nobody else knows how it is that the power spectra should be defined generally as a quantum operator. Nobody knows the answer to that. Nobody knew it at the time we wrote the paper. Nobody still knows the answer to that. And the only point that we wanted to make is that if you kept the usual definition of it, then and looked at this particular model, you would get logarithm of A corrections. And that statement is correct, and nothing that they did contradicts that. What they instead did is to say, no, you could redefine what you mean by the power spectrum in such a way that there wouldn't be any log A corrections. I don't disagree with that. Indeed, I could give you ways of redefining that. And in fact, I think it's a general theorem that if you regard the observables as something that you can play with and redefine that, any loop effect without anything, even measured loop effects, can be eliminated by changing what you mean by observables. For example, this isn't even something having to do with curved space. Let's take a known flat space effect like vacuum polarization in flat space, which is measured. If you say, no, what we mean by the electrodynamic force is not this scattering amplitude, it's really this thing. I can certainly change what I mean by S-matrix amplitudes in such a way as to completely eliminate that effect. And that's what they did. Now, maybe that's right. I don't know, and they don't know either, and they didn't prove that it's right. I'm not even sure what principle you would use to try and prove that it's right. And I must admit again that I felt a little bit badly used by their publicization of that because we had gone out of our way to say that we do not know what's the right way to define the power spectrum, the operator whose expectation value is represented by the power spectrum, and we are not claiming to have the one true right way of doing it, and they don't either, by the way. And I just, well, I hope that that's responsive to your question. If it isn't, please ask me again, and I'll try and be responsive to your question.
No, that was pretty much my question. Was like, would you like to comment on it? Yeah, that was what I was trying to clarify. Thanks so much.
Okay, you're welcome. By the way, one issue that has been raised not by them but by other people is the issue of gauge dependence, and that I think is a real issue. So people worry a lot about if you have loops of gravitons. Of course, the graviton propagator depends upon the gauge fixing, and you might worry that you're looking at some kind of a gauge artifact. Many people who don't want there to be any quantum corrections, I think will seize upon that. I think that they're barking up the wrong tree when they do that. But look, now we have a procedure for actually explicitly checking it, and we are doing it. We've done it twice in flat space. One reason that I believe very strongly that those people are just mistaken is that we can do calculations of modifications of gravitational force coming from loops of matter particles, no graviton propagators at all. This particular result, archive 1510-03352 with Soyun Park and Tomislav Prokopets, in which we looked at the effect of a loop of massless minimally coupled scalars on the Newtonian potential. And that has no gauge issue at all. So in order to believe what some people who like to believe that gauge dependence of graviton loops just is entirely eliminating these large logarithms, in order to believe that, you have to believe, well, this can occur with exactly the same kind of interactions in a matter loop contribution, but somehow magically when you do it with gravity, it just gives zero. And it gives zero to all orders. Well, maybe that's true. I haven't proven that it's not true, but I think that's straining credulity.
So sorry, maybe I can just then quickly ask you something with this gauge dependence. So I understand the point that, you know, this kind of large logarithmic corrections are probably not going to just go away because of some gauge effect. But if we go beyond the linear perturbation theory, if we include this kind of quantum corrections, do you expect the standard gauge relations or the standard gauge fixings that we use to be modified by when we go to one loop corrections? Would those have to be changed, the standard gauge relations that we use to define the gauge invariant variables? Would those kind of relations have to be changed?
Well, right now we don't know what are gauge invariant variables. If you know, please tell me.
No one knows. Yeah, right. No one knows. That's my question. So, do you expect them to be different from the standard ones once we include one loop effect?
They certainly will be different than the standard ones. Right now, what we're working on is a procedure that we have, which does, I think, connect to the standard ones. So it's a procedure, Shunpei will, by the way, tell you about this in June 2nd. and it really requires about an hour to do it justice. But what the procedure is basically is you construct what would be, you embed the theory that you really want to study in a larger theory with massless source and observer, massive source and observer fields. And then you study the scattering amplitude for an exchange force between a massive field that comes in here and exchanges whatever you're interested in, and then interacts with another massive field like that. You form exactly the same amplitudes that you would have used in the S matrix, but you don't actually calculate an S matrix, which you don't want to do because in cosmology it likely doesn't exist, and even if it does exist, it's not an observable. What you do instead is to use a series of identities that were derived by John Donahue to extract the leading long-range contributions of those scattering amplitudes, so that all of them, no matter how many points they have. So, for example, a typical correction would look like a box correction, where you have, say, you're looking at quantum gravitational corrections to a massless minimally coupled scalar exchange. So you might have a box correction where two of the massive scalars come in, they emit a graviton here, and then they exchange a massive scalar there. That would have sort of a 4-point structure where it has an intervening two massive scalars. Donahue derived a series of identities, not identities, but relations, simplifications, which will effectively shrink up those massive scalar propagators into delta functions, so that the leading long-range part of this amplitude takes the 2-point form. And then we showed that once anything takes the 2-point form, it can be regarded as a modification of the 1pi 2-point function. So this is a way of using the S matrix to purge gauge dependence from the linearized effective field equations. We have implemented this for the effective field equations of a massless minimally coupled scalar, of gravity corrections to a massless minimally coupled scalar, and also with Sanjib Katawal for gravity corrections to electromagnetism. So we have the gravitational correction to Maxwell's equation, and we've explicitly done this and shown in flat space background, where the calculations are much easier. We've shown that if you look at it in the general 2-parameter family of covariant flat space gauges, that all the gauge dependence sums up to 0 in the end. It's really an impressive demonstration, and I think it shows that that's the way of eliminating gauge dependence. I think that that will generalize in a straightforward way to de Sitter, and Dražen Glavan, Tomislav Prokopec, and Shunpei Miao and I are going to make a determined effort to do that this summer. And I think that that will work. So what that is and that, by the way, does connect up to known observables, that connects up to the known flat space observable of the S matrix. But it's important that it's being done at the level of the effective field equation, because in cosmology, there wouldn't be an S matrix, or at least it wouldn't be observable. So you want something that that would still make sense in cosmology, and I think this does still make sense in cosmology.
Thank you so much. Thanks.
You're welcome.
Next question is from Shravan Kumar. Shravan, please ask your question.
Hi, Richard. Thanks for a very nice talk. And I have a very small question related to previous answers. Basically, can you write S matrix in de Sitter? It's not possible, right? Or it's possible?
Well, it depends upon the field. So in some very nice work, let's see, me get the names right, Ian Morrison, Don Meroff, and Mark Shrednicki showed that for a massive self-interacting scalar on de Sitter background, you can indeed define a S matrix. There is, as far as I know,
for scalar field only, yes?
I'm sorry?
You say that only for scalar field in the given metric.
Well, that's the only thing that they've shown.
Yes.
So they've shown that for a massive self-interacting scalar, you can define an S matrix on de Sitter. It would not be observable for obvious reasons because no local observer could measure look at the whole asymptotic behavior to do that measurement, and they admit that. But as a matter of existence, if you just follow your nose and create it the same way you would do it in flat space, the construction goes through and it exists. Nobody knows what happens in more general theories. I spoke with Don Meroff about this once at one of the GR meetings. He believes that it likely will continue to work for electromagnetism. Nobody knows what happens if you take the scalar mass to zero or if you look at gravitational corrections. Those things have sort of stronger infrared I should not be too much inside baseball. The issue here is infrared problems when you take certain fields becoming massless. It turns out that photons actually behave better in de Sitter than they do in flat space. Gravitons and massless minimally coupled scalars behave worse. But again, nobody knows because nobody's actually checked this. And it can't really be the answer to what we want because it couldn't be an observable. Causality precludes you from doing the measurements you'd have to do to make it be unobservable.
Okay. Next question, please. More questions? I don't see any, so maybe I will ask. In fact, I have a couple just general questions. From general consideration, we know that sometimes fermions play a very positive role when we consider divergence problem. For example, for supersymmetric model, do you expect some positive role of fermion in the problem we discussed today?
I don't expect any. Actually, the first large graviton logarithm ever was found by Shunpei Miao in a calculation of graviton corrections to fermions. So we have worked on that, and it was the first ever large logarithm. So what she calculated was quantum gravitational corrections to the fermion self-energy. And then she used that to solve the effective field equation for the fermion mode function. And she found, just like these electromagnetic results, she found a result which caused the fermion wave function to grow like logarithm of A. Fermion loops, of course, do engender, the famous Fermi minus sign, which plays such a crucial role in the increased finiteness of supersymmetry. It doesn't seem to do much for us, but we're just beginning the investigation of this, and it's not impossible that it would have some important role in the renormalization group. For example, as you know, it can change the sign of certain key functions, right?
Okay. More questions? If not, one more question from me. Okay, this is just also some for curiosity. You considered a four-dimensional case. So what happens if we consider three-dimensional case, or we increase dimensionality, consider d-dimensional case, and maybe something interesting we can get using considering 1/d expansion. Can you make Richard, some comments about this?
Well, actually, I used dimensional regularization to do these calculations. I suppressed most of that, but let's see, some parts of it still exist. Here, for example, you might recognize
I
these
see.
as dimensional regularization results. I did the calculation in d dimensions, so I have the d-dimensional results. It turns out that the large logarithms of the nonlinear sigma models are independent of dimension. That is, they occur, the numerical coefficients change with dimension, but the fact that you're going to get a logarithm occurs in any dimension.
Okay. Thank you. Yes. I think it's too late today, especially in your at your home. How? What time is it now? Midnight.
12:44.
Oh, I see. So thank
So
you
if I
very
hurry
much.
back to my apartment, I might catch 5 hours of sleep before I have to get up for Chinese class.
Oh, I see. I see. For Chinese class. Okay. So, Richard, thank you very much for your very informative talk. Thank you very much. Thank you. So we closed our anniversary seminar today. Okay, let's meet
It was
into.
my pleasure. Thank you very much for your great questions and for having me here.
Okay.
Thank you, Richard. Thank you very much.
Thank you very much.
Please send your slides so that we can upload in the website.
Okay.
Okay.
PDF
Thank
files
you.
of them?
Sorry?
PDF
Also
files of
PDF,
them?
yes, PDF.
Yeah, PDF.
Yeah, PDF
Will do.
files. Yes. Yes. Thank you.
Yeah, you can send to Luca. So yeah.
Okay, so I'm logging off now.
Okay. Thank you. Bye, Richard.
Thank you.
Yes,
Bye.
thank you. Bye-bye.
Bye bye. Good night.
Thank you.
Thank you.
Thank you.
Especially thanks to Alexei Starobinsky, who asked,
Oh,
who
yes.
made many comments, yes, and asked many questions, yes.
He did so much for this field.
Yes, sure. I also,
Okay. Bye bye.
bye-bye.
Yeah, I'm closing it.